Hey, so today I'm actually going to record a video here just to start earthquakes so that we don't get too far behind. I was hoping that we could kind of coast in with the mountain building, but we already had our quiz, so let's go on ahead and start earthquakes, and we will kind of continue this when we get back next week. So earthquakes, this is a large slideshow here. It's our second topic before our test. So we'll have plate tectonics and earthquakes together. We'll have a test on that, and then we'll do like a little project on volcanoes, and that will round out our geosphere studies, and that'll be like kind of in the middle of the quarter. So earthquakes, to go ahead and begin here. As this says, we've got kind of movements within Earth's crust. So anytime the Earth's crust breaks and moves for some reason, it's going to be because of some kind of plate tectonic pressure, then that's going to be an earthquake. And I usually draw stuff on the board here, and I don't have a tablet that would make that really easy. So I'll probably redraw some of these very quickly, and remind me to do that if I don't, because one thing I like to draw is a stress-strain curve. It's a very common thing in material science and engineering, and we're going to talk about stress and strain. So it's kind of nice to see that in a really common kind of science and material science format. So the reason we have stress in Earth is just because there's pressure on things. Stress actually is the same like units as pressure. It's energy per unit volume or force per unit area. And I think that's maybe the easier way to think about it, force per unit area for many situations, because it's going to be like newtons per meter squared. So if you think about like it's easier to break a twig than a log, right? That's because there's smaller area on the twig. So if it's force divided by area, then you need less force to match the lower area of the twig than you would the large force to match the large area of like a log. So stress is the important thing there. Is the stress high enough for this to break? When you think about it in like a really large material instead of one that has like an obvious area there, then that's when it starts to make more sense to think of it as energy per unit volume, because how much energy has been put into crushing these two pieces of crust together before one of them is going to have to break. All right, I'm getting robotics text there. Sorry about that. So stress is, as it says, total force within a unit of area, or on a unit of area, maybe is a way to think of it. But another way is energy per unit volume. So we know about plate tectonics. This is just a reminder that these are all moving around because of the upwelling in the mantle and the convection cells in the mantle. And as it says, lithospheric plates press into the moving asthenosphere. So this stuff is moving. This is pushing down due to gravity, and then also against each other, where they will collide, for example, or be pulled apart at a mid-oceanic ridge. And this kind of friction keeps them in place. And also the stress will cause, as it says, strain, which is deformation. So strain is usually expressed in like a percent. So if something has been crushed down to, 97% of its size, then that would be a 3% strain. And strain is deformation, or bending is a way to think about it. So rocks, we don't normally think of being very bendy objects compared to metals. But rocks, you can probably hear my cat in the background. But these cats, good grief. These rocks, when they bend, they have some kind of strain there as a result of a stress. And we can talk about strain being in two different ways: elastic and inelastic, or plastic. So elastic deformation is something that is reversible. It's going to be a small amount. So you know how when you kind of like take like a plastic ruler or something and you bend it just a little bit, and then it bends back and forth. That is elastic. We also had an example in one class of the door stoppers that when you bend them and they go boing, 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 right? That's elastic deformation. The material that we call elastic, like elastic bands, is called that because when you stretch it, when you apply a strain, it will come back to its original shape. Right? So it will come back to the original shape, meaning it had a reversible deformation. So that was an elastic deformation. Inelastic or plastic deformation, and I think it's easier to say plastic so that you don't get confused between an elastic deformation or inelastic deformation. But plastic deformation is the opposite. It's where something is bent in a way that it doesn't recover from. So if you have a paper clip and you bend it, right, that has been a plastic deformation because it doesn't immediately snap back. It has been changed in an irreversible way. Even if you bend it back, and this is one of the things I like to draw the stress strain curves on, even if you bend it back to its original position, that was not an elastic deformation. That was a plastic deformation. And in fact, you've changed the stress strain curve in that case to make it more brittle, which is why if you go back and forth with a paper clip, eventually it breaks, right? Because you have actually changed the material structure there over and over again. And you've caused it to break. So plastic deformation, here it says it causes the rock to break. In general, rocks, because they're so brittle, if they undergo any amount of plastic deformation, they're probably going to break. But materials in general do not necessarily have to break to have plastic deformation. We just gave the example of the paperclip, right? The paperclip has bent, but it does not... the paperclip is bent and it's not going to return to its original shape, so it's not elastic, but it hasn't necessarily broken yet. Again, brittle things like rocks, more likely to just break the second they leave their elastic deformation stage. And everything always has an elastic stage and a plastic stage. The elastic stage is like bending less. If you bend anything a small amount, it'll go back. Plastic stage is basically once you've bent past that. And for different materials, that's a different amount, right? With the plastic ruler, you can bend it quite a bit before it's actually permanently bent. With material like rocks, you can do very little elastic deformation, and then it's going to go into plastic deformation. As it says, this reduces the internal stress back to zero when it breaks. And I'll show you that on the stress strain curve too on Monday. As after rocks snap, they're in new locations relative to one another. And what that's saying is this right here, where we have an elastic rebound. Basically, imagine this being on a transform boundary or a transform boundary, or what we would call strike slip fault. And then there's some kind of buildup of energy in here, that energy per unit volume, a buildup of stress. When that breaks, because it crosses the ultimate stress of the rock, meaning the ultimate, meaning like the final, the most stress it can withstand, then we end up with this slippage here. And it's really the grinding of these two pieces against each other as they bounce back. And that's the same thing as the boing, 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 boing door stop, right? When that happens, it's going to release a sound. And that sound, in the case of the door stop, is a funny, goofy sound that we all like to hear. In the case of an earthquake, it is the earthquake wave itself, right? That is going to be the sound of that rock breaking and kind of just elastically snapping back into place. For this kind of situation, different regions had plastic versus elastic deformation. Here along the fault where it broke, that's a plastic deformation, right? It's not returning to its original shape. But here and here, and I know my cursor's really small here, but here and here, those places have undergone elastic deformation because when it breaks, those regions do snap back to their original shape, so that you've got like this block here, returns to being this block here. And it's really just along the breaking boundary where there was plastic deformation here. All right, and as it says, this is now release strain, but since this is on a moving fault, this will continue to build up strain over time. So this can cause a lot of things. Here's just an example of an earthquake having moved part of a fence. Moving on, let's talk about the different kinds of stresses. Just based on the direction of these stresses, we can call them tension, compression, or shear. I use that word shear when talking about transform boundaries, but I never like wrote it on the board or anything like that. So tension is like a rope, right? It's being pulled taut. There is a stretching of this apart. When we look at compression, that is pushing things together, and it's being squished and usually comes out in the middle. And then shear stress is this idea of two things like rubbing against each other, as opposed to being pushed directly towards or away from each other. So they're not moving towards or away, they're just moving against each other. This all happens along faults. Now, faults are not necessarily the same as plate boundaries. There can be faults that are away from a plate boundary. Like, for example, there are a few earthquakes around, like between here and Arkansas, that are on a fault that is not in the middle of a plate boundary. And sometimes, like, you can have a fault that is, for example, a strike-slip fault on a divergent boundary, or you can have a tensional fault that is on what is mostly a convergent boundary, because faults are not the San Andreas fault, that's kind of an exception, but faults are usually much smaller than plate boundaries. Like, there's something that are a local thing, like this is a fault right here, whereas a plate boundary is a much larger idea, and they can interact with the surrounding plates, or one plate can interact with another plate in many different ways, causing some slight amount of, or local regions where maybe the rock's doing something different than you'd expect based on the large plate boundary. So don't confuse fault with boundary, even though they have kind of the same ideas going on with them. As it says, faults can range in size from fractions of an inch to miles in length. And some of the most famous ones are hundreds of miles. And all faults have, as it says, a hanging wall and a foot wall. And a way to think about it is the foot wall is shaped kind of like the doorstop, right? It's wedge shaped. The hanging wall is kind of wedge shaped too, but you could like hang down from it, right? So hanging wall, you could hang down from it. Foot wall, it's like a wedge that you kick with your foot, like our doorstop going into I-11. All right, I think I'm going to cover the normal types of, or the 4 types of faults real quickly, and just introduce them and then call that a day, and we'll continue this on Monday. Normal fault is where one, and it's helpful if you kind of put your hands together in that kind of position, where maybe where your palm of one hand is on top of the back of the other one, and then kind of raise it up to an angle, kind of like you see that normal fault. And then if you pull your wrists apart, you'll see that your hand that's on top of the other one slides down it. So this hanging wall in the normal fault slides down the foot wall, and that is going to be creating a tensional fault and creating very specific appearance of that fault. The reverse fault is going to be the opposite. So put your hands back in that same position and then push your wrists together, and you'll see that the reverse fault has the top one, the hanging wall, push up relative to the foot wall. So you've got a hanging wall that moves up relative to the foot wall as your wrists move together. Thrust fault is a special type of reverse fault. It's just at a shallow angle. So it kind of manages to push one side, the hanging wall, entirely over the footwall. And it's not as obvious what the difference is from this cartoon diagram, but when you see actual pictures later on of this, it'll be pretty obvious the difference there. And then strike slip is, of course, like we said, just a transform boundary, basically, or the same movement as that where there's shearing. All right, and we will continue on Monday. Maybe we'll review some of the stuff. Like I said, I'll draw the shear. What am I trying to say? Not strike slip, not shear. The stress strain curves up on the board, and we'll go over some of this stuff again. We'll also go over the quiz on Monday. All right, thanks, guys. Enjoy your weekend.